Good morning.
Wow.
Hello. Hello, viewers. I'm going to wait for at least 28 people watching before I start. Hope everyone had a nice weekend. Don't do that, kitty. No. Um, so, this is just an FYI. Oh, okay. My live chat is not working for some reason. Um, so just an FYI, my live chat is not working. So if you ask me a question, I can't see it. Here, let me try something else. Okay, I think I can see the live chat. All right. Can you see the live chat? Oh, someone wants to see the cat. I'll try to capture the cat. Give me a second.
Oh, Ivy. Ivy.
Unfortunately, I could not capture the cat. All right, so I'm going to go ahead and get started. I heard that we got an email that Google is having some trouble this morning, so this stream might be a little bit messed up this morning, but I'm going to try my best. All right, so let's get started. So the first thing I want to talk about is a concept from math, okay? And it's used in physics. So this concept is called area under the curve. Okay, so let's suppose I have a graph and it has a vertical axis and a horizontal axis, and maybe it looks like this, like that. So the area under the curve is the space between the line, or the graph itself, and the horizontal axis. Okay. So in this case, the area under the curve would be, so here's the horizontal axis, here's the graph itself, and so that would be the area under the curve. Okay. So you don't shade all the way down. You just shade down to the horizontal axis, and so the actual area of that, like the square footage, if you will, is called the area under the curve. Now, when a graph goes below the horizontal axis, like so, when a graph goes below the horizontal axis, you would shade up. okay? So again, here's the horizontal axis, here's the line, we're going to shade up. And then here, the graph goes above the horizontal axis, so we shade down once again, okay? So it's these areas, the square footage of these spaces is called the area under the curve. One important factoid, though, is that we count the areas as positive if they're above the horizontal axis, and they're negative if they're below the horizontal axis. Okay? So that is the, oh, there's, someone was asking about the cat. So there's the cat right there, eating. Ivan, what you doing, kitty? Okay. So it turns out, so here's the new fact for this lesson, important fact. Okay. So here's an important fact. The area under the curve of a velocity time graph is displacement. Okay? So if we have a velocity time graph and we want to know how far did something go, so remember displacement is how far did it travel from where it ended up, where it started to where it ended up. So let's say we have a graph like this that does this. This area is going to be the displacement. Okay? So I'm not going to prove to you why this is true. If you take my class next year, we talk a lot about it because that's a calculus-based class. But yeah, so that area is displacement. All right. So we have basically 4 important facts about motion graphs. Okay, so I'm going to write those down now. So depending on which graph you have, you want to, so we talked about position time graphs, and we talked about velocity time graphs, okay? And if you have a position time graph, slope is equal to velocity, and bendiness is acceleration. Okay? If you have a velocity time graph, the slope is interpreted as acceleration. Okay? And the area under the curve is displacement. Okay, so these are your key facts for motion graphs. Okay, if you're looking at a position time graph, you want to think about this column when you interpret it. If you're looking at a velocity time graph, you want to look at this column to interpret it. So pretty much the rest of this lesson is just going to be examples. So we're just going to do, I don't know, 2 or 3 examples of these graphs. Okay. So let's suppose I have a velocity time graph. So velocity in meters per second. Okay. And then time in seconds. And let's suppose that it looks like maybe this. So let's say that the entire graph is 20 seconds long. It goes from 0 to 20. Okay. And we have a this peak point right here corresponds to a velocity of 15 meters per second. And it happens at time 13 seconds. All right. So first of all, let's go ahead and interpret this graph. So what is happening in the first part of this graph? Well, in the first part, we can see that the velocity is increasing. It's moving further away from zero. So that means speeding up. And it's above the time axis, so that's a positive velocity. So basically you are moving forward and speeding up for the first part, okay? And then for the second part, we can see that the velocity goes from a positive number to 0. So that means that you're slowing down while moving forward, okay? So moving forward and slowing. So that is the second part of this. So I like to think about this kind of a graph. If we were to think of a situation that would have a velocity time graph like this, it might be if you're traveling between stoplights, okay? If you're traveling between stoplights, once the light turns green, you accelerate, you build up speed, and then you arrive at the next stoplight, and it's red usually, and so you have to slow back down to a stop. So you're kind of like, it's kind of like you start out at rest, and then you go like that, okay? So that's how we would interpret it in words. Let's talk about what is the acceleration at, let's say, 15 seconds. 15 seconds into the journey, so we can see that we have two line segments, and there's a transition between the line segments at 13 seconds, okay? So 15 seconds is after this transition. So I want the acceleration that corresponds to this line segment, okay? I want the acceleration that corresponds to this line segment. So this is a velocity time graph, and I can see that if I have a velocity time graph, slope is acceleration. So what this question is asking for is the slope of this second line segment, okay? So what is the rise of this second line segment? Well, it goes from 15 to 0. So that's a rise of negative 15 meters per second. And what is the run of this line segment? Well, it goes from 13 to 20. So that is a run of 7 seconds. So 15 over 7, that's what, 2.14 or something? Negative 2.1 meters per second squared. That is the acceleration at 15 seconds, okay? If I said calculate the acceleration at, for example, let's zoom in a little bit. If I said calculate the acceleration at 3 seconds, 3 seconds is right here, which corresponds to the first line segment, okay? For the next part, let's go ahead and calculate the total displacement. What is the total displacement for this 20-second long journey? Well, if I want displacement and I have a velocity time graph, displacement is area under the curve. So I'm going to shade in the area that I'm interested in. So here's the horizontal axis, here's the graph. So that is the area I need to calculate. And I can see that that shape is just a triangle. So the formula for the area of a triangle is 1/2 base height. So the displacement is going to be 1/2 times base. This triangle is 20 seconds wide, times height, which is, you can see this triangle goes from 0 up to 15, so 1/2 times 20 times 15. So that is 150 meters is the displacement during that. So basically, the distance between stoplights is 150 meters. All right. So that is an example. So we're going to do another example. Just lots of examples today just to make sure you guys are understanding this concept. Here's another example. And this is going to be a position time graph. Okay, so we have a position time graph. And let's say that the position time graph looks like this. Maybe okay. So we have a bendy portion for the first, let's say, 4 seconds. And the position at 4 seconds is, let's say, 2 meters. And then this is 5 meters, and that is 10 seconds. Okay. So my first question is, during what time interval is there acceleration? During what time interval is there acceleration? Well, this is a position time graph, okay? This is a position time graph. So how do we know if there's acceleration or not? Well, we go back to this table here, and we know that if you have a position time graph, acceleration is bendiness. Okay, so I'm looking for bendiness in the graph, and I can see that the bendiness happens from 0 to 4 seconds. So I would say, the interval 0 to 4 seconds. Okay, I don't care whether it's, closed brackets or parentheses, it's an open interval or closed interval, it doesn't matter. Okay. The next part I might ask is something like, what is the velocity? At, let's say, 9 seconds. Well, if I have a position time graph and I want velocity, going back to my table here, position time graph, velocity is the slope. Okay? So what I'm asking for is the slope at 9 seconds. 9 seconds is right about here. So I want the slope of this line segment. All right? And I can see that that line segment extends from 4 seconds to 10 seconds. So that's a run of 6 seconds. And I can see that the displacement, the position goes from 2 to 5. So that is a rise of 3 meters. So that's going to give me a velocity of 0.5 plus 0.5 meters per second. All right, so that's an example of a position time graph. Let's do another velocity time graph. Maybe one that looks like this. Let's see. Okay. So it kind of looks like this. Let me put some numbers on the axes here. Let's say that is negative 20 meters per second. This is 5 seconds. This is 10 seconds. This is 17 seconds. And that is a velocity that corresponds to, let's say, 25 meters per second. So this graph is not to scale, obviously. I'm just making up the key numbers, okay? So the first thing I might ask is describe the motion. So let's describe this motion in words. Okay? Well, the first thing I notice is that this velocity time graph, first of all, it's a velocity time graph, okay? So that means that I am in the second column here, where slope is acceleration and area is displacement. And I can see that it's made up out of 3 line segments. 3 line segments, so that means that my description is going to have 3 parts to it, okay? So for the first part, so basically we have from 0 to 5 seconds. What's happening? Well, our velocity is a negative number, so that means we're moving in the negative direction or backwards. But we can see that the speed is going from something that's pretty fast, 20 meters per second, to 0. So it's slowing down, okay? So this is from 0 to 5 seconds, it's moving back, but slowing, okay? What's happening between 5 and 10 seconds? Well, the velocity is stuck at 0. So from 5 to 10 seconds, it is at rest. It's not moving for that entire time period. Okay? And then from 10 seconds to 17 seconds, we can see that the velocity is positive. The velocity is positive, and it's going from 0 to a, let's zoom in just one more. It's going from 0 to a more positive value, so that's speeding up. So this is moving forwards and speeding up. Okay? So now let's get quantitative about this graph. So there are 2 words that are used in science a lot: qualitative versus quantitative. Qualitative means describe it in words. Quantitative, it has quantity, means you're describing it in numbers. Okay, so this was a qualitative description of the of this motion. So now let's give a quantitative description. So first of all, I might ask something like, what is the total displacement? For this motion. So the total displacement, if I have a velocity time graph, total displacement is area under the curve. So I'm trying to calculate the area under the curve. So I have this area, which is going to be a negative area, okay? And then this area, which is going to be a positive area. I keep seeing cat's in the live chat, so I'm wondering if the cat is behind me. So basically, to get my delta x, I'm going to have minus the area of that triangle plus the area of that triangle. Now, this spot right here, it has no area under the curve because the graph and the horizontal axis coincide, so there's no area between those. So, if we look at that first triangle, it has a base of 5, so 1/2 times 5, and a height of 20, because it goes from 0 to negative 20. For this second triangle, it has a base of 7 and a height of 25. So that's 7 times 25. So now I'm going to use my calculator, plug that in. So that's 50. I don't know why I typed that into my calculator. And then 0.5 times 7 times 25 minus 50. So we get the displacement for this journey is 37.5 meters. Okay. Yes, this is my handy dandy calculator. I actually had a really tragic event happen last year. I've had a calculator for basically since college. Even before college, I think I had it in high school. So I had the same calculator for, well, how many years has it been? I guess over 16 years. And like 17 years, I had this calculator. And I was fast on it. I was just, I could type in stuff so fast. And I spilled water on it, and it broke. And now they don't make that kind of calculator anymore. So I'm super bummed. As another question, let's go ahead and calculate what is the acceleration at time 2 seconds. So 2 seconds. 2 seconds. The first segment goes to 5 seconds. So 2 seconds is about right here. So what I'm asking for is the slope of the very first line segment. Okay. I can see that the slope, it rises from negative 20 to 0. So that's a rise of 20 meters per second. And then the run is 5 seconds. So that is an acceleration of plus 4 meters per second squared. All right. We're going to do one more example, and then we'll transfer over to Zoom. Let's do one that looks like this. Take that back. Do one that looks like this. So here is the graph. It looks like this. So here's 0, and it does this. So here is 4 seconds. Here is 12 seconds. This value is -5. This value is -12. So for this entire motion, the velocity is negative. So it's always moving back. Now, if we describe this motion, we have 2 line segments, so our description is going to have 2 parts to it. So in that first part, we can see that the velocity is negative, so it's moving back, but it's staying steady at -5. So this, for the first segment, we have a a particle that is going backwards at a constant speed. All right. For the second part of this, we can see that the speed, or the velocity, which already started negative, is becoming more negative. It goes from -5 to -12. -12 is faster than -5. Okay. So that means that it is speeding up while going back. Going back, speeding up. So that is the description of this motion. Next, I would like to calculate the displacement. If you have a velocity time graph, the displacement is the area under the curve. Okay. Now this one's a little bit trickier. This area, I will always give you areas that can be sliced up into rectangles and triangles. Okay. So the area under the curve is going to be this space right here. So it's asking for that area. And how you break up this area is up to you. Okay. You could think about it as a rectangle and then a trapezoid. However, I see this, when I'm looking at this shape, I see it as this rectangle, okay, and this triangle. So I'm going to think about the displacement as a rectangle and a triangle. These are both going to be negative areas because they are below the horizontal axis. All right, so I have my area is going to be negative this rectangle and negative the triangle that's right here. Okay, so what is the width of this big rectangle? It's 12 wide and it's 5 it's 5 down, so that would be 12 times 5, so that's 60. So I have -60 for that first rectangle. And then for the triangle, I go from 4 to 12. That's 8 wide. And then the triangle goes from 5 to 12, so that's 7. Okay. So this is -28, so I get -88 meters is the displacement. Let's keep the live chat clean, everybody. I'm not even sure what that means, but I can guess. Let's keep the live chat clean, please. All right. So that is my lesson. Pretty quick lesson for today. So what we're going to do is go ahead and move over to Zoom, and we'll work on today's quiz. Okay. Let me just double check that I didn't. Hang on, before you leave, let me double check I'm not forgetting something that I was supposed to talk about today. Okay, cool. Yeah, I covered everything. All right, so I will see you on Zoom.